By the end of this video, you will be able to explain what seismic waves are and the information they provide about the Earth and earthquakes, and you will be able to recognize, identify, and contrast the motion of the two types of interior or body waves.
So today we want to demonstrate what happens to the energy that is released during an earthquake. We know that from elastic rebound, which is the demonstration we just did before, that energy is released. This energy is what defines an earthquake. When we talk about earthquakes, it's a release of energy from the rocks in Earth's crust or lithosphere. So energy is released from a particular point along a fault. That point is called the focus. All energy is then transferred through the crust or lithosphere from that focus. So if we can imagine, again, our bend and snap, that point where our dowel breaks would be considered the focus if that's where our fault is. That energy is released. We hear it in the sound of, we hear it in terms of sound waves when we did it with this, but there are other kinds of energy waves that are created when an earthquake occurs, when that stress is released and their energy is transmitted. That energy travels through the Earth. It travels through the crust, it travels through the mantle. Some of it makes its way to the core, and it actually moves all along, all to other sides of the planet. Some of that energy does travel along the surface as well. So we have different types of waves. We have waves that travel inside the Earth, which we call body or internal waves, and then we have our surface waves. We're here to talk about those interior waves, those internal waves, those body waves, because those are the waves that are very important to geologists, the geologists that study earthquakes, seismologists or geophysicists. They tell us about the source of the earthquake. Where is that focus? Where, or the word that you may be more familiar with, the epicenter, which is usually what gets reported in the news, the epicenter. So that's what we're interested in. And understanding those internal waves and how they travel can tell us about how to locate that epicenter. And that's very important for geologists. It's also important to inform the public as well because we want to remain safe. So we are going to demonstrate these particular type of internal waves. We have a metal coil here, and we're going to send Christian down to the other end of the room to get an idea of how these waves travel and how they travel through the crustal rocks. We're going to demonstrate the two types of waves. There's actually two waves that are detected by a seismograph. A seismograph is a tool or instrument that geologists, seismologists use to record and detect these seismic waves, seismic meaning generated from an earthquake. And the first one to arrive is our P wave, right. And P stands for primary wave because it's the first wave to arrive. It's the fastest traveling wave. So it's released from the focus and then it travels through all points in the interior of the Earth until it's recorded on a seismograph. It is a special type of wave. It is a compressional wave. And so what it does to the rock as it moves through it, as it transfers through it, is that it compresses and extends the rock. So it travels in a straight line, and we're going to demonstrate that here with our coil. So Brian's making a nice compression part of the coil here. This is kind of our compression area. This is essentially the crest of the wave. And what we want to do, what I want to do, is actually time it to see how long it takes for this compression wave to travel to Christian. It's going to bounce off his hand. We know it doesn't hurt, right? Right. And it's going to come back pretty quickly back to Brian, and it's going to keep on going until the energy has dissipated. So we'll do this on 3. So, okay, and I'm going to time this compression wave. So see if we can watch this compression travel through the coil, hit Christian's hand, and then come back to Brian. So here we go. So 1, 2, 3. Yeah, I got 1.14 seconds. So that's a pretty fast traveling wave. You know, it travels in a straight line, more or less, along this coil. So it's compressing, it's alternately compressing and extending. if we don't want to remember the words compression or extension, we can remember two P words, push, pull. It's pushing the rocks together and then pulling them apart. That's got to be pretty tough on a rock to, as the P wave travels through it, to be compressed and extended like that. The second type of wave that we're going to demonstrate is the S wave, S for secondary. And secondary, not just because it's the second wave to arrive at the seismograph station. It travels a little bit differently than the P wave. We saw the P wave travels in a straight line where it's a compression tension. Here, the S wave, well, it kind of makes an S-shaped. It travels like a sine wave curve. Sorry for the trigonometry algebra reference, for those of you that didn't like that. We can also remember the word shear, because if we think of the blades of a scissor that move back and forth against each other, they move up and down, and that's how an S wave moves. It shears the rock, so it goes up and down, kind of like a snake, as a snake would slither across the ground, making that S shape. So lots of S words, S for secondary, S for shear, S for snake or slither, just like P has the primary, push and pull. So we're going to demonstrate an S wave, and so Brian's going to create a S wave curve just by shaking the coil up and down, and I'm going to time how long this wave takes as well. So ready? 3, 2, 1, go. So I got 1.31 seconds. So it takes a little bit longer for this S wave to travel. And that we think about that, it's because what does the wave actually have to do? It has to go up and down as opposed to a straight line, just like for the P wave. So it has a little bit longer path to travel, and that's why it's the second wave to be detected on a seismograph as opposed to the P wave, which is the first. So we can come back for the conclusion of this. We also know a couple things we learned about P and S waves. We know P waves can travel through any material. They travel through solids, liquids, and gases because all of those can be compressed and extended. S waves, as we learned, do not travel through liquids. And so as a result of understanding P and S waves and how they behave, just like in our coil, we know that S waves do not travel through the outer core. And this is how we learned that our outer core is liquid, right. We also know, we also used our understanding of P and S waves to understand that as we go past the crust-mantle boundary, several miles into the mantle, something starts to happen to the mantle. It gets a little, it's not so solid anymore. It gets a little melted. The heat starts to increase, and it starts to be partially melted and starts to move. And in tectonics, we know that that's the top of a very important layer called asthenosphere, right? So above that is the brittle lithosphere, and below that is the partially melted asthenosphere, and that's what allows tectonic plates to move. So we know that S waves slow down quite a bit, almost disappear at that point because the partial melt prevents the S waves from traveling through. But P waves, they slow down a little bit because of its liquid, but they still continue on through. And so this tells us about the interior of the Earth. This is something that geologists strive to know because we want to know about a place we can't see and actually drill down into. So it tells us about what's all the way down, all the way to the very core of the Earth, very center of the Earth. But it's also important to know about earthquakes, these events that impact lots and lots of people, where they have occurred, and of course we want to remain safe from earthquakes. So P and S waves. So P waves are compression, tension, push, pull, the primary wave, and the S waves, like a snake, like a sine wave, they are shearing, they are going up and down, they are the second wave. They have a little longer path because they're going up and down as opposed to a straight line.